In this example, we're asked to use the convolution integral to find the response of this undamped single degree of freedom oscillator, where the forcing in this case is a rectangular pulse of duration capital T and of amplitude of f naught. We're asked to look at the case of initial conditions of 0. So by using the convolution integral approach, what we have here is x naught times cosine omega nt plus the initial x dot naught divided by omega n sine omega nt plus the convolution part, which is 1 over m omega n 0 to t of sine omega n t minus tau, forcing f of tau d tau. Again, for 0 initial conditions, we lose these terms outside of the integral. And we're going to break this up into two parts. One, when we're looking at a response time somewhere when the pulse is turned on. And in this range, our forcing within the integrand here is going to be f naught, which is a constant. I'm going to do a simple change of variables here. I'm going to let z be defined as the difference between t minus tau, so therefore the integration over tau is the minus of the integration over z. This also says that the lower limit on the tau integration, when tau is equal to a 0, it says that z is going to be equal to t, and the upper limit of integration when tau is equal to t, it says that z is equal to a 0. So from this we see that our convolution interval term is going to be equal to 1 over m omega n. There's going to be a negative sign sign in front from here. The integration goes from t, z equal to a t, up to z equal to a 0 of sine omega n z, and then again the forcing f naught comes out on the outside because it's a constant of dz. The integration of sine is going to be a negative sign sign, which is going to make that plus, with another 1 over omega n, so this becomes omega n squared, and this becomes cosine omega n z. The evaluations are z equal to t on the bottom and z equal to a 0 on top. So in this case, what we end up with is f naught over k, m omega n squared, that's k. And then what we have here is a 1 minus cosine omega nt. So this is what's for the solution that's valid whenever time is between 0 and, I'm sorry, I labeled this. This should be a capital T. There's no A here. And so while the pulse is turned on, this is the response. Now let's look at for the time after the pulse is turned off. So this is t larger than capital T. In this case, our f of tau is defined in a piecewise way. It goes from f and f naught, while tau is somewhere between 0 and capital T. And of course, it's a 0 for tau larger than capital T. Therefore, our convolution integral becomes 1 over m omega n. We have an f naught coming out as a constant, so this is 0 to t of sine omega n t minus tau d tau, and then the integration from t to small t of sine omega n t minus tau, but in this region the forcing is equal to a 0, so we simply lose that last term. So we're left with this convolution integral being f naught over m omega n, integral from 0 to t of sine omega n t minus tau d tau. What we'll do as before is we'll redefine our variable of integration in terms of z, where z is the difference between t and tau. The integration over tau becomes the negative the integration over z. The lower limit when tau is equal to a 0 corresponds to z equal to t. The upper limit when tau is equal to a t, it says that z is equal to 0, just like it was before. So this says then that our x at t, our convolution integral then, becomes f naught over m omega n. The integration, the first one here, or the only one here, it goes from z equal to t all the way up here to, I'm sorry, the upper limit here was not small t. I'm still stuck back on the one before. When tau is equal to big T, it says here that z is equal to t minus big T. So that's what we get here on the top, t minus big T. Sine omega n z dz. The integral of sine, we've done that before, that's a minus sign sine with a 1 over omega n on the outside. That's a cosine omega n z, and that goes from t up to t minus big T. So therefore, what we have is I'm sorry, there was a minus sign here, and then a minus and a minus makes that a plus. So the integral of the sine function is the negative sign sign in front. So this becomes f naught over k, and we evaluate cosine omega n z at t minus big T minus cosine omega n small t that looks like this. So this is what's valid for times after the pulse is turned off, where the expression we had before was valid while the pulse was on. So in summary, what we have is x of t is equal to f naught over k, 1 minus cosine omega n t, and this is the time during which the pulse is turned on. What we got last here was f naught over k, cosine omega n t minus t, minus cosine omega n t, and this is valid for time after the pulse is off. How does this actually look? Well, what I did was I just took these two functions and I plotted them together for various values of the duration of the pulse t. And I compared the value of t to the natural period of response. That would be t sub n, and I'll write that down here in just a bit, is that Tn is the natural period, and that's equal to 2 pi over omega n. And what I have here in the first picture is when the ratio of the time duration, t, when that's a quarter of the natural period of the free oscillation. What we see here is the blue section here, just to the left of this dot, is the response we have during the time that the pulse is on. The red, which occurs after that, is the ringing that we get even after the force is off. As we increase that up to ratio up to 0.5, we see that the blue here represents the response during the time the pulse was on. It's reached its maximum value there of 2. Whenever the period of the pulse, the duration of the pulse, and the natural period of response are one and the same, then what happens is it reaches one full oscillation. It reaches a point here where x and x dot are both at 0. The force is turned off. It stays at rest from there on down. Whenever we make the duration t larger than t sub n, in this case 1.25, the blue here shows the response during the time that the pulse is on. The red shows the ringing which occurs after this. So for any duration t larger than 1 compared to the natural period t sub n, we're going to be reaching a maximum response of 2. For values less than that, we see that the response here is going to be something less than 2. So these are just observations that we make about the response, and this is going to be useful information to us later on in the course when we talk about shock response, that is, response to the system for short duration, high force value inputs. And we're going to exploit this in order to understand what that shock response is. But here, this example is just to show how the convolution integral works for this square wave pulse.